Hello everybody, welcome to my channel. Module 5 here, CCNA 2, switching, routing, and wireless essentials. So before we begin, we're going to go back down memory lane to one of our older videos. So take a look at this real quick. Let's take a look at this. So if you remember in one of my previous videos, I believe I mentioned that you just started a new job. I think we call this Marvel Studios, all that good stuff. Notice it's a 3-story building. Boss says, come on in. You're going to be in charge of this. There's 3 stories, but I want all of the communications on each one of these to be different, right? All these floors, I want them different. So it takes you down to the closet and you see this absolute mess. Like an absolute dreadful mess. And you're thinking in your head, like, what am I going to do with this? Boss says that half the stuff doesn't even work. Maybe a router works. Not sure. Things are all crazy. And you tell them, like, hey, I need to buy some new stuff. Can you please buy me some new stuff? Boss says, okay, cool. Know what? No problem. We'll get you new stuff. As a matter of fact, we're going to get you a switch. So you get the switch. You get the rules. We want to section off certain parts of the building. So you take the switch and you VLAN these areas on these switches, which creates individual mini switches on a virtual interface using one physical device, right? All that's good to go. Now, speeding forward, things are cooking. Everything's going good. Boss is having a good time. You're making some good money. He's making some good money. Boss says, you know what? I want to get another switch. Matter of fact, I want to get 2 more switches. Because if something were to break down, or if one of my original switches were to break, how is everything going to work, right? We still need to be able to communicate with the world. I still need to be able to have processes coming in and out of my building. So I need that redundancy. So he buys 2 more of these, and you need to make sure you hook them up, right? They have to be hooked up. And then another task, and this is kind of off the wall topic. When you're done, I want my networking closet to look like this, which is nice and just beautiful. Nicely ran cables. Everything looks nice. Everything's punched down like it's supposed to. All that good stuff, okay? So again, you had 1 switch to work with. Now you're going to have 2 more switches. The boss gives you 2 more switches because he wants that redundancy. 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 What am I being right now? I am being redundant because I keep repeating. You want that redundancy, right? In case something were to break, you have a backup, or if something were to get turned off, or all that good stuff, okay? All right, so let's get into this. Ladies and gentlemen, welcome to Spanning Tree Protocol Concepts, Switching, Routing, and Wireless Essentials, CCNA 2, and let's get into this right now. Okay, so the purpose of this module, we're going to explain STP, how it enables redundancy on a layer 2 network. We're going to explain the common problems in redundant layer 2 network switch networks. We're going to explain how STP operates in a simple switch network, and we're going to explain rapid PVST operates. You know, that's the Cisco version. All right, purpose of STP. This topic covers the causes of loops in a layer 2 network and briefly explains how spanning tree protocol works. Redundancy is an important part of the hierarchical design for implementing single points of failure and preventing disruption network services to the users. Again, there's the CIA triad. Disrupting network services. Send me an email. I want to know what part of the CIA triad does that affect. I want to know what that does. So redundant networks require that addition of physical path. So again, going back to the scenario, okay, the addition of physical paths. By the boss adding 2 more switches, he's creating 2 more physical paths, right, for that redundancy. But let's finish reading here. But the logical redundancy must also be part of the design, right? So having alternate physical paths for data to traverse the network makes it possible for users to access network resources despite the path disruption. So Ethernet LANs require loop-free topology with a single path between any 2 devices. So, and we're going to get more into this. You'll see this. So we want things to be loop-free, meaning that we don't want crazy things to happen. So we'll get more into this here. Let's keep going here. Now, STP, what it's designed to do, essentially is designed to prevent broadcast storms. That's what it does, right? It's a loop prevention network protocol that allows for redundancy while creating a loop-free layer 2 topology. So we have all these switches, right? This is kind of what we've been talking about. We have all of these wonderful switches, and we want a loop-free topology, right? We want everything to move properly like it needs to. So STP logically blocks physical loops in a layer 2, preventing frames from circling back and forever. Okay. STP, it logically blocks the loops. Okay. Very important. Doesn't physically pull it out, it's logically. Okay. So everything is still connected, right? We want everything to still be connected. So it just logically blocks it. So take a look at this. STP compensates for a failure in the network switch by recalculating and opening up previous block ports. So you can see we have redundancy here, and I'm going to show you a packet tracer on this in a little while, so you'll be able to get this in more detail. But all these devices that are connected, these are all the designated ports, right? And we're going to get into the root bridge and root port, the root port, all that good stuff here in a second. But again, STP compensates for a failure. So in this example, there's an X through this. So essentially, this line is logically broken. So the best route to get to PC4 is to go through this switch, and on out, right? Because here goes another question, and I want an email from this. Hopefully you're paying attention to this video. What does the switch do when it receives a new frame? Send me an email on that one too. All right, so issues with redundant switch links. Path redundancy provides multiple network services by eliminating the possibility of a single point of failure. When multiple paths exist between two devices on an Ethernet network, and there is no spanning tree implementation on the switches, a layer 2 loop occurs. So, going back to my question that I want you to send me an email on, what does a switch do when it receives a frame? Specifically when there's other things connected to the switch. What is it supposed to do? What does it do? Okay, layer 2 Ethernet does not include a mechanism to recognize the element, and eliminate endless looping frames. Okay, we're talking about broadcast storms. Both IPv4 and IPv6 include mechanisms that limits the number of times a layer 3, so we're talking about a router, right, or a multi-layer switch. Layer 3 networking device can retransmit a packet. A router will decrement the time to live in every IPv4 packet and the hop limit field in every IPv6. When these fields are decremented to 0, the router will drop the packet. Okay, that happens on layer 3. Ethernet and Ethernet switches, layer 2, have no comparable mechanism for limiting the number of times switches retransmits layer 2 frames, right? So there's nothing to stop it. It just keeps going, right? So STP was developed specifically as a loop prevention mechanism for layer 2 Ethernet. So without STP enabled, layer 2 loops can form, causing broadcast, multicast, and unknown unicast frames to loop endlessly. This can bring down a network completely, right? This is very big. So STP is very important. Okay, and later on in the video, we're going to get into all the different variations of STP, but STP is very, very important. Okay, very important. When a loop occurs, the MAC address table on a switch, MAC address table, will constantly change with new updates from the broadcast frame. So when information comes in, and there's the answer. When something comes in on that switch, that MAC address table is going to update. And it constantly updates. It keeps updating. If it gets information, it's going to update again. If it gets new information, it's going to update again, right? An unknown unicast frame is when the switch does not have the designated MAC address in its MAC address table and must forward the frame out all ports except the ingress port, right? So if it comes in the ingress, it won't go out the same ingress. It's going to egress out. Broadcast storms. This is a big one. A broadcast storm is is an abnormally high number of broadcasts overwhelming the network during a specific amount of time. Okay. Broadcast storms can disable network within seconds by overwhelming switches and end devices. Broadcast storms can be caused by a hardware problem such as a faulty NIC or from a layer 2 loop in the network. So that's another reason why STP exists, right? So when all of those switches are getting new frames and updating MAC address, it's just a never endless loop. That's why we have the STP, okay? Now, let's get into this. Layer 2 broadcasts as a network such as ARP requests are very common, right? What does ARP do? Send me an email on that one. Layer 2 multicasts are typically forwarded the same way as a broadcast by a switch. IP version 6 packets are never forwarded as layer 2 broadcasts. Why is IP version 6 packets not forwarded? Maybe because they use like a global, maybe, I don't know, something like that, right? A host caught in a layer 2 loop is not accessible to other hosts on the network. Additionally, due to the constant changes in the MAC address table, the switch does not know, the switch does not know out of which port to forward the unicast. So it has no idea. So it's going to flood it, right? It's going to send it out. To prevent these issues from occurring, the redundant network, some type of spanner tree must be enabled, right? So we have to be able to mitigate some of that. So the spanner tree algorithm. This is the algorithm for spanner tree protocol. STP is based on an algorithm invented by Radia Perman while working for Digital Equipment Corporation in 1985. Okay, 1985. Her spanner tree algorithm creates a loop-free topology by selecting a single root bridge. Okay, it's the first time you heard that here, root bridge, where all other switches determine a single least cost of path. Okay. STP prevents loops from occurring from configuring a loop-free path through the network using strategically blocking state ports. Okay, again, not physically blocked, logically blocked. The switches running STP are able to compensate for the failures by dynamically unblocking previously blocked ports and permitting traffic to traverse to alternate ports. So they all speak to each other. All right. So this is just essentially talking about more about the algorithm. We'll just get into this here briefly here. So selecting the root bridge, okay, we're going to block redundant paths. STP ensures that there is only one logical path between all destinations. One logical path. It's going to create a loop-free topology, and it's going to recalculate in case of a link failure. So when all of those switches are hooked up, right, when all those switches are hooked up, if one link were to fail, it's going to get picked up, right? They're going to talk to each other. They're going to say, hey, I realize that this route is not working anymore. Let's enable this route that was disabled. We're going to enable it automatically so we can have the redundancy, and we're good to go. We're going to keep rolling here. All right, STP Operations. Okay, so before we get into STP Operations, I want to show you this picture of the wonderful San Francisco Bay Area. Shout out to San Jose. You can't see it on this picture because it's south of here. That's where I went to college, San Jose State. Go Spartans, San Jose. Love San Jose, 408. Let's go. All right, anyway, let's take a look at this here. So we have the San Francisco Bay Area. And right now, for the purpose of this, we're going to focus on this area right here. Up in the San Francisco area, Oakland area, San Rafael, all that, okay? Now, you're going to see these little arrows right here. You'll see these little red arrows going in different directions. You got this arrow going this direction. You have a blue arrow going other directions, okay? What I want you to know is that these little arrows, these are bridges. These are bridges that lead to the different areas of the Bay Area, okay, especially up in the San Francisco Bay Area. But for the sake of this, what we're going to do is I want you to change your thinking of these bridges. We're going to basically call these bridges Ethernet connections, okay? We're going to call them Ethernet. So these are all Ethernet connections right now, all right? Okay, so in these areas, what I'm going to do is I am going to take this color here, and I'm going to create a switch. We'll call this a big switch right here. This is a big switch. These are switches. These are all layer 2 devices. Okay, these are all layer 2. These are all switches. All right. So we have the San Francisco switch. We have the San Rafael switch. And then we have like the Berkeley, Oakland switch. Okay. All right. Quick question. Right now as it sits, like I told you, we have these arrows. These are Ethernet cables. They're all connected to the switches, right? Let's say, for example, you're on a trip and you're traveling up the 101 freeway, coming through San Bruno, all that stuff. And you want to get to San Rafael, California. San Rafael, right? You see on the map, probably the quickest way to get there is to go over the Golden Gate Bridge. We're going to take this switch. We're going to go through this Ethernet cable onto this switch and then get to San Rafael, right? That's probably the quickest path to get there. But what would happen if this decides to break? What if that bridge is not physically, we don't want that to happen. What if that bridge logically has been disabled, right? What's the best way you're going to get there? That is correct. You are going to head out this Oakland Bay Bridge through Berkeley, and you're going to hit another bridge outside of Richmond to get to San Rafael, right? That's what's going to happen. Vice versa. Let's say if you're coming from Oregon and you need to get to Berkeley. Okay. I come in, I get to San Rafael switch. I see the best way to get there is to go through this Richmond area to get to the Richmond Berkeley switch, and bam, I am here and I'm where I need to be. Okay? Now, let me show this to you. See if I keep everything up here as much as possible. Okay, so we already determined that we have layer 2 switches. Okay, layer 2 switches. What is a switch designed to do once it receives a brand new frame? And what does it do? What specifically does it do to the MAC address table, right, of all these switches? So, same example. What if I show up to the San Francisco switch and none of these connections are logically broken? All the connections are good. Again, what's the role of a switch when it gets a new frame? You show up in San Francisco, you say, hey, I need to get to Richmond, California. That's where I need to go. Help me out. The switch says, yeah, I know how to get there. You go out of this port. But here's a new frame. The switch is actually going to send it out this port as well. And now this switch gets a new frame, and this switch gets a new frame. What is the job of the switch when it gets a new frame? It's going to broadcast out to the ports. So guess what? As soon as it shows up, this switch is going to send out a broadcast and say, hey, I need to get to San Rafael. And this switch freaks out and says, wait a minute, I'm getting the same broadcast, and you're brand new. I'm going to send you back out this switch. Here, I'm going to let you get to your destination because you know how to get there. But you just got a new frame, so you're going to send it out to all the channels. Now, this switch, let me switch colors here, this switch just received a new frame. Now it's going to send it out its ports. Now this switch just received another new frame, and it's going to send it out all of its ports. And now we have a broadcast storm. We have an endless loop, right? We have an endless loop. So we don't want that to happen. So let's take a look at this. So steps to a loop-free topology using the algorithm spanning tree protocol. So it builds a loop-free topology in 4 steps. So the first thing that's got to happen, it's got to elect a root bridge. Okay, we need a root bridge. It needs to happen. We need to elect the root ports, and we need to elect the designated ports, and we need to elect the alternate ports, the ones that are going to be blocked. During this algorithm, STP functions, switches use what's called BPDUs, okay, Bridge Protocol Data Units, to share information about themselves and their connections. BPDUs are used to elect the root bridge, the root ports, designated ports, and alternated ports. So there's a negotiation that happens that basically says, hey, we all can't do the same thing all at once. So one of us is going to have to bow down to the other, while the other one is the workhorse. That's what has to happen. Each BPDU contains a bridge ID that identifies which switch sent the BPDU, and the BID is involved in making many of the STA decisions, including the root bridge report. So it sends information. So as soon as it's hooked up, right, the switch sends information to the other switch and says, hey, this is my ID. I can do the same thing you can do, but here's my ID. We need to elect to figure out who's going to do what. The BID contains a priority value, the MAC address of the switch, and the extended system ID, essentially, which that's the VLAN, right? The lowest bid value is determined by the combination of these three fields. So let's take a look at this picture here. Let's go to this one here. So STA designs a single switch as a root bridge and uses it to reference point to path the calculations. All right, so let's take a look. We have three switches, kind of like in the picture I showed you, right? We have three areas of the Bay Area, right? Three switches. As you can see, the lowest priority is in this BPDU, and this bridge ID is 24577. So because this is 24577, we see a priority value of 32769, 32769. These are the same. This has the lowest bridge ID priority, so this one is going to be the root bridge. So these ports right here are going to be essentially the designated ports, right? Both of them are designated ports. So the idea for that is to send information away from the root bridge, right? It's got to send information away from the root bridge. All right. So out of both of these, which ones is going to be the root ports? Do we know which ones are root ports? Not yet. Let's take a look into that. All right. So because the default BID is 32768, it is possible for two or more switches to have the same priority. That's what we kind of just discussed there, right? In this figure, all switches are configured with the same priority. Here, the MAC address becomes the deciding factor as to which switch becomes the root bridge, okay? So we figure out the root bridge. The switch with the lowest hexadecimal MAC address value is the preferred root bridge in this example. Switch 2 has the lowest value of the MAC address and is elected as a root bridge for the spanning tree instance, right, for switch 2. The priority of all the switches, 32769, the value is based on the 3269 default bridge priority value and extended value, which is the VLAN. So it's pretty much you add the VLAN number to the value of 32768, which gives you 32769. All right. So how are we going to determine the root cost of the path? How are we going to figure out which path to take? We're in that San Francisco Bay Area. We got to figure out which path we're going to go through, right? So when the root bridge has been elected, because this is the part 2, right? When the root bridge has been elected for a given spanning tree instance, the STA starts determining the best paths to the root bridge. So it needs to know how to get to that root bridge as fast as possible, right? Because we want high availability. We want to get that data there. Okay, so the path information known as the internal root path cost is determined by the sum of all individual port costs along the path from the switch to the root bridge. So essentially it's the speeds. The way this connection speeds are determines how that cost is. When a switch receives the BPDUs, it adds the ingress port costs, so how fast it's coming in, right? And, cost of the segment to determine its internal root path cost. The default port costs are defined by speed at which the port operates. Okay, so if that port is operating at 10 gigabits, okay, we're looking at a STP cost of 2, our STP cost of 2,000, and so on. If it's 1 gigabit speed, 4, 100, 19, as you can see, the faster the gigabit speeds, the cost is a lot lower, right? Because we want to get that data there as fast as possible. Although switch ports have a default port cost associated with them, the port cost is configurable. So you can change that. We can change the configurations on those. The ability to configure individual port costs gives the administrator the flexibility to manually control the spanning tree paths to the root bridge. All right, so let's take a look at this. this diagram here. After the root bridge has been determined, the algorithm is used to select the root port. Okay, so we figured in this port, we have the root bridge. This had the lowest priority, right? But we need to figure out what the root port is, which means the port that's going to get to, right? The way it accesses those ports, right? Every non-root switch will elect one root port. So here is, we have a root port here, which is connected to the switch. This is the root port that's going to that switch. Okay. Okay, we said root port close to the switch. Okay. The overall cost is known as the internal root path. Okay. The internal root path cost is equal to the sum of all the port costs along the path of the root. So, essentially, this is a cost. This is a cost, and it equals a number, and whichever the lowest is going to be the fastest. So, in this example, okay, path 1, okay, 19 by 1, okay, 19, that's a cost of 19. Path 2 is essentially 2 19s, okay, which equals 38. So the path 1 is going to be preferred. This is going to be the quickest path to get there. We don't want to go all this way. This is going to be the quickest path to get to that switch. So elect designated ports. Every segment between two switches have one designated port. The designated port is a port on the segment that has the internal root path cost to the root bridge. In other words, the design port has the best path, the designated port has the best path to receive traffic leading to the root page, the root bridge. So we have a designated port. Remember, both designated ports going out away from the root bridge. Here's a root port as it's coming in. Designated port going out. Okay, root port coming in, as you can see. All right, and you see we have a nice little topology. But one of these is going to be broken though, right? That's essentially how the spanning tree works. But it's working because we have these designated ports and we've determined which one is going to be the root bridge. All ports on the root bridge are designated ports. That's what we just discussed. If one end of the segment is a root port, the other end is a designated port. So if this is a root port, this has to be a designated port. If this is a designated port, this has to be a root port. If this is a designated port here, this must be a root port, right? That's just kind of how we're looking here. On segments between switches where neither the switches in the root bridge or the root and the port of the switch with the least cost path of the root bridge is a designated port. Okay. All right. So let's look at the alternate ports. If a port is not a root port or becomes a designated port, then it becomes a alternate. All right. So let's go back to this. Let me go back to this really quick. Let's read this really quick. All ports attached to the end devices are designated ports. If one on segments between two switches where neither the switches is a root bridge or the port of the switch with the least path cost root bridge is a designated port. Okay, so we have a designated port. It's attached to a root port. Designated port attached to a root port. So can we have two root ports? The answer is no. This is going to become an alternate port. And this is all negotiated, right? This is all negotiated. If a port is not a root port or a designated port, then it becomes an alternate port or a backup. Alternate ports are all discarding blocking state, preventing loops. So essentially, this should be a root port, but it's not because the root port has already been designated. So it's going to block that port. All that information is going to be blocked out. So root is going out, designated is coming in, designated going out here into this root, and so on, right? Ethernet frames, all other inter-switch ports are in forwarding state. This is the loop prevention part of the STP. So they're all the ports, they all forward. They're just going to forward the traffic out. So when a switch has multiple equal cost paths to root bridge, the switch will determine the port using the following criteria, right? Lowest sender, BIDs, the lowest priority, and the sender port ID. All right, so let's take a look at this topology and this network that I have set up here. All right, so we have 3 switches. We have some redundancy here. All right, 3 switches. we have 4 end devices. All right. So if you want to make the reference that I referenced the San Francisco Bay Area, this could be the San Francisco switch area. This is the San Rafael switch area. This was like the Oakland area. Okay, the Oakland area. Due to this package, you can probably see it right off the bat. We can already see, all right, that we already have this orange light right here. So we know that right off the bat, this connection is probably going to be an alternate connection. This one has been logically blocked already to prevent, right, those loops. So remember I told you the election process happens when these switches boot up. When you start connecting them, they start figuring out who's going to do what, and they start figuring out who's what, who's going to do all this, who's going to handle the root bridge activities, all that good stuff. So that stuff is already how all the negotiations happen. So let's take a look at this. Let's go into this switch right here. We're going to go into this first switch here. And what I'm going to type in is show interfaces status. Okay. This is also a good command that you can type in when you're trying to figure out which VLANs you're going to configure each switch ports and all that stuff. So as you can see, I have my speeds running in full duplex on all these ports here. Here's my speeds, and they're connected. So we're dealing with fast Ethernet 1, 2, and 4. Okay, 1, 2, and 4. So we know we have things that are up. Now, let's figure out, let's see here. We're going to type in show spanning tree. Now we have a lot of different information here. Okay, remember this is the stuff that happens in the election process. Right now, this switch, okay, we have port 0-1 is a designated port. 0-2 is a designated port. So if I'm looking at my packet tracer, it's probably going to be one of these two, maybe. But take a look at this. 4. That's my alternate port. Look at the status. BLK. It is blocked. That is this port right here. That port has been blocked, right? And then we have our root port. So all information coming in this switch is going to go out the root port, right? So what did we say in our previous slides? Can there be 2 root ports on the same line? That's incorrect. If there's a root port, that means there must be a designated port, right? This must be a designated port. Listen to the rules. If there's a root port, on the other end of that line must be a designated port. So let's take a look at this switch. Let's go to this switch. Same thing. We're going to type in show interface status so we can see what's connected. And we only have 2 devices. We have 2 cables that are connected. We can see that logically as well, right? We have 2 connections running at full duplex, okay? We have fast Ethernet 1 and 2. Let's get some more data on that. Let's type in show spanning tree. Ooh, what do you got here now, folks? Check a look at this. All right. Now we have fast Ethernet 2, designated port. It is in the forwarding status. Fast Ethernet 1, designated port. It is also at the forwarding status. And look at the cost. So, ladies and gentlemen, this is our root bridge. Right? Take a look at the priority values. They are the same. MAC addresses, they are the same. So this is forwarding information out. Okay? It is supposed to give information. So anything that comes out, it is going out. It is going out. So both of these are in a forwarding state. Right? So anytime it gets anything, it is kicking it out. It doesn't want it. Right? It's going in and out right away. This is our root bridge. This is our root bridge. So if both of these ports are our designated ports, okay, if these are our designated ports, what must this port be right here? That should be a root port, right? Let's take a look at that. Let's get into this switch. So let me close this down just a little bit more so you can see. I'm going to type in show spanning tree, and voila, there we go. And as you can see here, we have our root port, cost of 19. There's our root port going out. We have a designated port. So we have 3 designated ports, which makes sense. 3 designated ports. This is the root port, right? So we have root, designated, right? If this is root, this cannot be root. That's why this connection is closed down. All right, so now let's really do a little more in depth here. Let's take a look at this. Because remember, we need redundancy. Let's say, for example, okay, I'm actually going to go into, let's go into this switch here. Okay. Let's just say, for example, since we're dealing with Fast Ethernet 2, let's go to Fast Ethernet 2. I'm going to go into 0-2. I'm going to go into this connection and I'm going to shut it down. Okay, I'm going to go into this connection and shut it down. I'm going to shut down one of the designated ports on this root bridge. Okay, I'm going to shut down O2. What is going to happen? What's going to happen? Take a look here. What's going to happen? So I shut this connection down. And remember, this was a designated port. Okay? This used to be a designated port. What do you think is going to happen here? Or what do you think is happening right now? Right now, data probably cannot get out because this is supposed to be a designated port. But we need redundancy. I turned this off. Yes, if you said it correctly, you probably are right. What's going to happen is after the negotiation process happens again with spanning tree, we should see this one turn green, which means this, okay, this will probably become the root bridge. There it is. It just turned. So let's take a look at this switch now. There we go. So now we have the root port here, and now we have the designated port. But folks, which one is the root bridge now? This is probably still the root bridge because we still have redundancy, right? Because now the information is going to go through here. Let's take a look at this switch. Let's go back to this switch. Show spanning tree. Okay, we have our root port, right? And let's go back into the one that I turned off. Let's go here. Let's go exit. Hit again. Show spanning tree. So we have no root bridge, right? Because one of the switches has decided, we turned off one of the links to the switches. But what I wanted to show you was the redundancy here, right? You turn off one of these links, the other side is going to pick up. You turn off one of the links, then one of the other switches, one of the other connections is going to pick up, right? It's going to give you an alternate route. Very similar to if I'm in the San Francisco Bay Area, okay, and this bridge to get to San Rafael is busted, I am going to have to go a route through Oakland area to get to San Rafael, right? Or if it was vice versa the other way, right? So that's an example of how that works. This is spanning tree. We're trying to prevent the loops. And you can see with the different bridge IDs, remember all the different costs that happen within these lines determines which one is going to be the root bridge. Now for right now, what I'm going to do is I'm going to turn the root bridge back on. So let's go config T, and I believe it was 2, right? So we're going to go interface fast Ethernet 0-2, and I'm going to type in no shut. Okay, there we go. So I turned that link back on, and as you can see right away, because this was the root bridge, it automatically changes from back to the alternate port. Okay, so let's take a look at the evolution of spanning tree protocol. So there are a lot of different versions of spanning tree protocol, okay? So many professionals generically use spanning tree to refer to various implementations of spanning tree, such as rapid spanning tree protocol, multiple spanning tree protocol in order to communicate spanning tree concepts. So there are different types of spanning tree protocols. They just call it spanning tree protocol, right? That's just what they call it. So the one that's owned by Cisco, I think I mentioned earlier, Cisco switches, they're running a 15.0 later. They run what's called the PVST version of spanning tree. It's like a updated more version of that. It makes the conversions happen faster. All right, we want things to happen a whole lot faster because we want high availability. Let's read this third bullet really quick. Because the two protocols share much of the same terminology and methods for the loop-free path, the primary focus will be on the current standard and the Cisco proprietary implementations of STP and RSTP. That's kind of what we just kind of talked about, right? The rapid spanning tree protocol. So regular spanning tree just was implemented earlier in the years, not as fast, took a while for it to really kick in. Rapid spanning tree just gives you high availability, right? It gets everything turned back on right away, helps out the conversions, gets things relinked as quick as possible like it needs to. All right. I'm not going to get into this. This is some of the different versions. I'll let you take a look at this. There's just a lot of different years when things happen per VLAN spanning trees. So we've been working on those VLANs. You can set those spanning trees for those VLANs, right? All that good stuff. Now, 802.1W is the protocol for RSTP. Okay, the original was 802.1D as in David. Okay, while retaining backwards compatibility, the 802.1W STP terminology remains primarily the same as IEEE 802.D. Okay, so it's all in that same family. It's all in that same family. It's kind of like, some may disagree, but it's kind of like command prompt versus PowerShell, right? PowerShell is like a Hercules version of DOS command prompt. Command prompt is like the old school version, right? RSTP increases the speed of recalculation of the spanning tree when the layer 2 network topology changes. So it just, like I said, it just makes it a whole lot faster. There are only 3 port states RSTPs that correspond to the 3 possible operation states in SP. 802.1.D is disabled. Blocking and listening states are merged into unique 802.1W. Okay. So root ports and designated ports are the same for both. And as you can see here, they just kind of work in conjunction there. All right. So look at the port states. All right. You can see the different states basically tells you if it's on, if it's in the forwarding state, receiving, all that good stuff. An alternate port has an alternate path to the root bridge. The backup port is a backup to the shared medium, such as a hub. A backup port is less common because hubs are now considered legacy devices. We don't use hubs anymore. Hubs are over. Hubs send out broadcasts every single time. We don't ever want to use a hub. Instead, you want to use a nice switch. Okay. So port fast and BPDU guard. So when a device is connected to a switch port or when a switch powers up, the switch port goes through both the listening and the learning states, right? So why do you think that is? What did I say earlier in this video, right? It needs that negotiation election process happens, right? Each time waiting for the forward delay timer to expire. This delay is 15 seconds for each state for the total of 30 seconds. This can present a problem for DHCP clients. Interesting. Remember, DHCP, Data Host Connection Protocol. DHCP, send an email if you don't know what it does. DHCP obviously designed so it gets your IP information to your computer so you can get out to the internet. Like it's like getting a brand new house, you need address information so you know how to get out there, right? And I can see where this could be an issue. So this could present problems for DHCP clients during the discovery of DHCP server because the DHCP processes may time out. So a brand new computer fires up. If there's multiple switches, it may not know where to get the DHCP information from. The result is that the IPv4 client will not receive a valid IP4 address. Okay. Tell me, you can also send me another email. If a IP version 4 information self-assigns its own IP address, what is that? And what is the name of that IP address? Very good. Send that to me. When a switch port is configured with port fast, the port transitions from blocking to forwarding state immediately. avoiding the 30-second delay. So we want the port fast. We want that enabled. So we want things moving as fast as possible, right? Because we don't want things to delay out. A port fast enabled switch should never receive BPDUs because that will indicate that the switch is connected to the port, potentially causing spanning tree loop. So we don't want it to, right? We don't want that election process to happen with that port because we want it to go out as quick as possible. Cisco switches support a feature called BPDU guard. When enabled, it immediately puts the switch into a air disabled state upon receipt of BPDUs. Well, it protects everything from loops. Okay? All right. All right, that concludes Module 5. Hope you guys enjoyed this video. Make sure you like and subscribe to the YouTube channel. Follow me at TandyIT, and I will see you on the next video.